Hello, this is Concrete Path and the lecture for your problems related to that analysis and design of flanged beams. Let's go take one by one the problems we are going to take one by one. Let's go for those problems. Let's go one by one. So taking the problem number one, let's take the first problem we have. It's saying that get the moment of resistance, of this T-beam, of the T-beam, and the T-beam is in this fashion. This is your T-beam. We have an effective flange width of BF equals to 1000 millimeters. 1000 millimeters. We have a DF, that flange thickness equals to 100 millimeters, and we have a width of that web that we have equals to 300 millimeters. And there is effective cover also. 50 millimeters. Effective cover of 50 millimeters. And the small d is 450. Small d is 450. This is 450. And we need to get the moment of resistance. Now we had to assume, that where is the neutral axis. So how can you start it? So we have to first assume that neutral axis is somewhere. Let's assume that first case, if I assume that neutral axis is in flange portion, that is xu is less than or equals to df. Now if I take that part, I would say that the equation, that means the part contributing to C forces, if this is the neutral axis somewhere in the flange portion, that means there is the C forces are contributed by those concrete, and T force is contributed by that steel. That means we know that the equation for this one is equals to that C force is equals to 0.36 FCK, and the actual width that is contributing for those C forces, that is capital BF, that is total BF of 1000, and we have this actual XU, and T force is 0.87 FY AST. Now to get the moment of resistance, what we need to get? To get the moment of resistance, we need to get actual location of neutral axis. So for that, we have to say summation of forces in that section in the horizontal direction is equals to 0. So C equals to T, and from that you have to get the location of XU, and after that we can get the moment of resistance of the section. And there might be one more data provided to you. One more data is provided to you, that's area of the steel. That's 1963 millimeters square, and the concrete, that's of M20 design strength. This characteristic strength, and the characteristic strength for the steel is 415 megapascals. Let's take that problem. So I'm going to equate C force with the T force. So I would say 0.36 FCK, and BF into XU is equals to 0.87 Fy into AST. So this is the equation we have. So we have to substitute those values, and we can get the value of XU equals to 98.44 millimeters. Now once I got the value of XU, I don't have to substitute it. Directly. I have to first say that check now whether your XU is less than DF. We have to check this now. So I would say your DF is 100, your XU is less than DF. That means true. The assumption you had earlier, that is true, because we earlier assumed that neutral axis is in flange, and I got the value of XU as 98.44, and that is lesser than 100. So I would say that assumption is true. So moment of resistance would be corresponding to XU. Now it won't be corresponding to XU again, so we have to check one more thing. What's that? Can you guess? What's that? Once I got the XU value, now we have to compare it with the limiting condition. That's K times D. And for the grade of Fe415, we have this 0.48 value of K, and the depth here is 450 millimeters, and this value is equals to 216 millimeters, and that is greater than XU. So which means that section is under reinforced. section is under reinforced, so I can take the moment of resistance corresponding to actual value of XU, that is 0.36 FCK, and BF, that is 1000 millimeters, into actual value of XU 98.44, then we have D minus 0.42 XU, D minus 0.42 XU actual. So you can solve that, and your moment of resistance would be equals to 289.63 kilonewton meters. Okay, this was the very easy problem we have. So let's go for the second one. Let's go for the second one. We have to get the limiting area of the steel, AST, and we have to get the limiting moment of resistance. We have to get these two values of the flanged beam, of this flanged beam. So the flanged beam dimensions are BF equals to 1000 millimeters, and we have effective cover also same 50 millimeters. Effective cover 50 millimeters. Effective cover of 50 millimeters, and we have this small d 450. We have width of that. This is also 300. Similar to previous problem. And the thing is that we have not provided the steel. We have not provided the steel. Okay, and we need to get the limiting value of steel. What should be the limiting condition for the that area of the steel? And we also need to calculate limiting moment of resistance. And corresponding to these two, we have to say what is the limiting location of neutral axis. Is that 0.48 times 415, 450? Can we say that? Axial limiting equals to this one, KD, and that is 216 millimeters. 216 millimeters, is that 0.48 into 4.5 is 216 millimeters? Yeah, that's 216 millimeters. Now we need to say what kind of problem is this? We had studied here in the case that calculation of limiting moment of resistance, we had studied that if the case of dF by D was greater than 0.2, and one more case was that if the dF by D ratio was less than 0.2. So after that, we had to see which of the equations we had to use. So we need to see what is the value we have for the dF by D ratio. So calculate the ratio of dF by D. So we need to compute this ratio. dF by D equals to 100 millimeters, and small d is 450. This is equals to 0. What is this value equals to? Let me calculate. 100 divided by 450. That's 0.222. 0.222, and 0.222, it's greater than 0.2. So I have to use the equation of YF equation. I have to use that. This is our equation. We have to convert it into equivalent thickness of the flange, having the constant stress, having the thickness of YF, and we have the constant stress value of 0.45 FCK. Can you calculate that value? Do you know the equation now? You have to use the equation of YF. So I would say limiting moment of resistance is equals to 0.36 FCK B XU limiting, and this is your BW XU limiting, and D minus 0.42 XU limiting. And after that, we have C2 force. C2 force is 0.45 FCK, BF minus BW, and we have that we have that YF also here, and we have that lever arm of D minus YF by 2, and we have to substitute value of YF as 0.65 DF plus 0.15 XU limiting. So let's substitute those values. 0.36 FCK. Let's substitute those values, and we can have that equation. We can have the calculation of limiting moment of resistance. So mu limiting can be solved as 0.36 FCK BW 300. BW is 300, and axial limiting is 216, and D is 450 minus 0.42. Axial limiting is 216. Okay, then plus 0.45 FCK, then BF minus BW, BF minus BW. Then we have YF. The value of YF is 0.65 times DF, 0.65 DF plus 0.15 axial limiting, 0.15 axial limiting. Once we got this, we have that lever arm also, lever arm D minus YF by 2, DF, that's YF by 2, YF by 2. Okay, this is your YF, and we have to divide it by 2. So finally you solve those values. So that data we need to solve. So finally mu limiting is equals to mu limiting 413.87. Now second part of the problem is that you need to get the area of the steel, limiting area of the steel. How can you get the area of the steel corresponding to limiting condition? How can you get that? So I would say, once I know the limiting condition of neutral axis, axial limiting, I can equate C force with the T force. I can equate that C force with the T force, and I can solve that now. I would say your C force is 0.36 FCK BW XU plus 0.45 FCK BF minus BW. Then we have that lever arm of, we have that YF, that equals to 0.87 Fy AST corresponding to limiting condition. And we have similarly here limiting also, limiting condition. Corresponding to limiting condition we need to calculate. So this data is already available here. This data is already available here. Let's remove this one. I would say 0.36 FCK BXU limiting. This is your XU limiting. Then we have to remove this part. We have to remove this part. Let's erase this part. So this is your 0.36 FCK BXU limiting. Then plus 0.45 XU, 0.45 FCK BF minus BW. Then we have that YF equals to 0.65 DF plus 0.15 axial limiting. Okay, this part is already over, and we have to remove that lever arm. We have to remove this lever arm, and that we have to equate total C force equated to total T force of 0.87 Fy into AST limiting. So get the value of AST limiting equals to 199.177 millimeters square. Now we need to select a few bars. If I select that 25 diameter of the bar, if I select 25 diameter as the diameter of the bar, and I am going to say what is the total number of bars I can have for the diameter of 25. So I would say total area 2991.77 divided by 0.25 into pi into 25 square, 6.0948. So that means I am getting value of n equals to 6.0948. So I had to use more than that. So that means I have to select a diameter that is more than this one, because bars are also more, and I have to select a diameter such that it's more than 25. If I select a diameter as 28, so let's select the diameter as 28. I am going to see how many bars we need for the diameter of 28. Let's have that same value data here, only we need to replace that 25 square as 28 square. So we need 4.85. Corresponding to this value, we need 4.85 bars. But this is also odd number of bars. If I provide 5 bars, so that's odd. So that's odd number of bars. So we can either we can provide 5 number of bars. We can provide 5 number of bars for this one. Maybe we can provide 5 number of bars. Maybe we can provide 5 number of bars. I think that's okay if I provide 5 number of bars. Or either you can provide 5 number of bars, or you can convert, you can have 6 number of bars. If I have 6 number of bars such that 4 bars are of 28 and 2 bars are of 25, let's try to see this combination also. Always try to have a combination that's having even number of bars. Let's try to have this combination. Let's see how much area we have for this data. Let's write that 0.25 into pi into 4 number of 28 square plus 2 number of 25 square. So I'm getting 4.75 mm square. This is the area provided for these number of bars. And what is the area required? So we would see that your area is more. You are providing more area here. If I compare it with this one, so this is more area we have. So we should select a lesser value. So I should select a 25. Let's select a 20 diameter bar here. Now if I select a 20 diameter bar, let's try to select a 20 diameter bar. So I would say we are going to select 4 bars of 28 phi and 2 bars of 25. Let's try to see what is the value of the area of the steel. So I would say the same data is solved here, and this comes out to be equals to 3091.3 millimeters square, where the total area is pi by 4, 28 square into 4 plus 2 into 20 square. So I think this value is suitable. This is feasible value if I compare it with the required value, limiting condition. I think this value is feasible. So finally, I would select out of all those combinations, I would select one that is in even number of bars and that's also still closer to the limiting condition. That means our economical value should be there. I should not use large number of steel. This is large number of area. More area I am providing here. The difference here is almost 500 millimeters square. So I need to go for this design. I would prefer this one. So I had to provide 4 number of bars of 28 phi, 2 number of bars of 25 for this design. So finally, I can show those bars also. Let's try to have that diagram. If this is your flange, this is your web, and there is some effective depth of D. There's some effective depth of D. Okay. Let's say this is some effective depth of D. Let's say this is the center to center distance between those bars, such that few bars are above this line and few bars are below this line. If this is one bar, this is one more bar, there is 4 bars placed at the bottom. So I would say 4 number of 20, what you call as 28, and 2 number of 25, and this is our D. This is our D, center to center between those D, and this is your effective cover of 50. And if I say what is the clear cover, and we need to say what is this spacing there. I would say this is some 10 millimeters, and this is 28, and this should be clear cover. But the thing is, you should ensure that clear cover is greater than 25 millimeters for M20. That clear cover should be at least greater than 25. So clear cover should be at least greater than 25 millimeters. If the clear cover is at least 25 millimeters, 25 plus, or I would say the diameter of the bar, that's 28. What this value equals to? This is 53. This is 53. So this is the thing here. This is the critical thing here. Yeah, I think that इतना तो चलेगा, इतना तो चलता है यार. I think so. So that's all detailing. You have to select that clear cover is also ensured. And your diameter of the bar is also have to place, and there is spacing between the bars also. Some bar, let's say this is 10 millimeters. If this is 28 and this is some clear cover, this should be always more than 25 millimeters. So you are actually your D is going to change. Actually, I would say finally your D is going to change based on this condition. D is going to change. Because of this condition, your D is going to change. Your D is going to change for the given condition. For the limiting condition, if you want to solve it, your D is definitely going to change. but we will still calculate as per the problem. Your D is actually going to change now. So this is the final solution, I would say, but D is going to change. Okay, let's take that third problem. Let's take the third problem we have. So if I say that D is going to change, that means I have to show that I have to show finally that uh, that that clear cover is should not be. I have to ensure that codal provision also. I have to show this codal provision that this should be minimum value of 25. This should be minimum value of 25 for M20, minimum of 25. After that we have this power of 28. So so that actual D becomes lesser than 450 millimeters. So you have to show that actual D. What is the actual D now? D final. So you have to show that also. Okay. Finally, go for the third problem. Go for the third problem. Third problem of that. So we have this one. Moment of resistance we need to determine for the beam. Moment of resistance for the beam. Okay. Where your AST is equals to 2591 millimeters square. We have 4 number of bars of 25 diameter, and we have 2 number of bars of 20 diameter, 20 millimeter as diameter, and the dimensions of the section is equals to, this is BF 1000, and we have DF equals to 100, DF equals to 100. After that we have width of web BW, that's also 300. Similar to previous case, similar to previous case, similar to previous case, similar to previous case. Similar to previous case. That means the thing is the clear cover is not ensured in these problems. I think I can say that if this is 450, it's mentioned that D is 450. In this problem, it's saying that D is 450, and total is what you call as effective cover is 50. D is 450. That means if I am placing now 6 bars, if I am placing 6 bars, so I have to say what is the D value. It's saying now in this case it's saying that D value is, so if I when I saw the diagram, it's saying that D value, we have to take the D value up to the bottom level. It's saying we have to take the D value up to the bottom level. So if I take that D value corresponding to bottom level, then there is no problem. There is no problem with that. Let's say we have 4 bars, 1 2 3 and 4, and we have 2 bars at the top, and it's saying that this is the center to center of the bottom bars. So it's saying that D is the center to center up to the bottom bars, D. And from that perspective, I would say your D is 450 millimeters. There's no worries with that. There's no worries with that. D should be 450 millimeters. And this part we have to ensure this is what you call as 50 millimeters. And clear cover would be corresponding to that. That would be clear cover would be corresponding to 25 millimeter bar. I would say clear cover is equals to 50 minus 25 by 2, that is 37.5. So that is greater than 25. So for that, in that perspective, I would say your D is not, the D value is okay. But for the previous problem, we can I said that we can take the D value, corresponding to the centroid of the bars, I said that D value would be somewhere here, and based on that your clear cover was not ensured. So finally you would take D corresponding to the at the center of bars, Okay, let's take this problem now. Let's take this one. Let's take this now. We need to get the moment of resistance of this problem, of this section, such that your characteristic strength for your materials is that concrete is having M20 and steel is having Fe415. Okay, use LSM method, limit state method. So what is the first thing we need to get? Is it talking about limiting condition? It's not talking about limiting condition. So we don't need to get df by d ratio. So this ratio is used for calculation of limiting moment of resistance. This is not used for this problem. Whenever there is moment of resistance, we have to go for the actual case of 3/7 of xu, and that where the neutral axis is actually. So let's assume that that neutral axis is in the flange. Let's assume that neutral axis is in the flange. So this is the assumption. So start of the solution is that assume xu is in the flange, because we don't know where the flange neutral axis is. So if I assume that neutral axis is in the flange, then I can say that C force equals to T force. I would say if my data of AST is provided, can I get the location of neutral axis from this equation? If I know that if I know the value of AST, I can get the value of that XU location. I would say 0.36 FCK BF XU is equals to 0.87 FY AST. And I can substitute those values that are given to me. That is 0.36 FCK BF XU equals to 0.87 FY AST 2591. So I can get the location of neutral axis. XU equals to 129.93 millimeters. Is this true? Now we have to check that whether this is true as per the assumption. So I would say your flange is only 100, but your XU is greater than DF. So this is false. That means this is false. Assumption is not true. So we need to take the second case that that means XU is in flange. Actual value of XU is in the web. The value of XU actual is in the web. And one more assumption is that we have to take that. I would take that 3/7 of XU that is greater than DF. If I say that 3/7 of XU is greater than DF, I have to check whether this is correct or not. If I substitute initial value, see, either you have to take actual value of XU corresponding to actual neutral axis. You have to solve for that one. That means you have to solve for C1 plus C2 equals to T1 plus T2. Then you have to check, then get the value of XU. After that, you have this 3/7 of XU. That is actual as per the calculation of actual location of neutral axis. But if I start that by some assumption that I'm going to take that XU value as the value of XU I got from this part. See, I got this part of XU corresponding to that. I assumed neutral axis was in the flange, and if I still solve this, if I still use this value, but this is not correct, I would say this value of XU is not correct. But still, if I solve for 3/7 of XU, add this value of XU, and I would say what is this value coming out to be? If I still solve for this, and it might help me getting the guess of that actual location of neutral axis. Let's see how I'm going to use this value of XU. That is not correct, but still it might help me in getting the in saving time in calculations. Let's see how. If I say that 3/7 of XU is equals to how much? What is this what is this value of 3/7? That XU 129.93. If I write 3/7 of 129.93, what that value equals to? 3/7 of 129.93, that is equals to 55.6843, and I have to compare it with the DF. DF value is 100, so I have to compare it with the DF. I would say this value is less than DF, and when the condition is that if there is 3/7 of XU less than DF, which of the equation we have to use? Is it equation of YF or is it equation of DF? Which of the equation we have to use? That means DF is bigger as compared to 3/7. That means we have to use this equation. That's converting into equivalent thickness YF. So we have to use the equation of YF. So I have to use the equation of YF. If I solve for the value equation of YF, let's solve for the equation of YF. So I would say total C force equals to T force, and get the location of neutral axis. So I would say 0.36 FCK BW XU and plus 0.45 FCK and BF minus BW. Then we have that YF. What is the value of YF? We have YF is equals to 0.65 into DF plus 0.15 XU. So we write 65 plus 0.15 XU. That we have to equate with the T4, 0.87 FY AST. Area of the steel was provided to you, 2591 millimeters square. 2591. So I can solve it a linear variation that of XU. So I can solve that XU comes to be equals to finally 169.398 millimeters. Now I need to check it because I have assumed that your neutral axis is in the web. That is true. That is true because of the first assumption we said it was in the flange, and that was not true. That means this is definitely in the web portion. But second assumption is that 3/7 of XU we have to check with respect to DF. So if I now solve 3/7 of XU, that's actual value of XU now. So if I solve 3/7 of XU actual, and that is equals to 3/7 of XU. Let's solve for that. 3/7 of 169.398. That's 72.6 almost. And is that less than or greater than DF? DF was 100. That means 3/7 of XU is lesser than DF. So what was the assumption we had earlier? What we assumed? We assumed that DF is, yeah, this is not the assumption. Assumption should be that DF, this was the assumption, sorry, because we are calculating for the YF calculations. So assumption was in this way, that this was DF that was greater than 3/7 of XU. Because of that, we take the equation of YF. So our assumption was that DF is more with respect to 3/7. And we also got that DF is more with respect to 3/7 of XU. That means assumption is true. Assumption is true, so we can proceed further. So actual value of XU is corresponding to 72.6 millimeters. Now that's corresponding to 169.398. 169.398 millimeters. That's your actual value of neutral axis. See, what was the guess we take it earlier? What was the use of that first value of XU? See, this was not the correct value of XU. 129 is not the actual. 169 is the actual value of neutral axis. But this value it helped us to take a guess that if I take 3/7 of this particular value, that came out to be this value 55, and this was less than 100. Then I said that there's a possibility that the actual value of XU is such that your DF is greater than 3/7 of XU. So it helped me to take the equation of YF directly. Otherwise, I might have solved for the equation of DF. Then if the true equation was not true, so I had to go for the third step also from that onwards. Okay. Now once we got the value of XU, finally, once it is true, so we need to proceed further. Now we need to compare with the XU limiting equals to K times D equals to 0.48 times 0, and the value of D was 450, that is 216 millimeters. And comparing these two values, I would say limiting condition is more. Limiting value is more. So that's more than XU actual. So under reinforced section. Under reinforced section, that means moment of resistance of the section would be corresponding to actual value of XU is equals to 0.36 FCK BWXU D minus 0.42 XU and plus 0.45 FCK BF minus BW and D minus, yeah, we had to use that equation of YF because our assumption was in terms of YF. So because we assumed that there is a rule of YF, so we have to write here YF and D minus YF by 2. And we need to solve now actual value of YF. That was 65 plus 0.15 XU. XU was 169.398. 398. So this is the value of YF. Get the value of YF. YF comes to be equals to YF comes out to be equals to 90.409 millimeters. Let's substitute the values for this one to get the moment of resistance. 0.36 FCK, BW, XU, and D minus 0.42 XU, actual, and we have this 0.45 FCK, and we have this BF minus BW, and we have this YF also 90.409 into D minus 90.409 divided by 2. So that's your calculation for moment of resistance. So final value would be equals to 369.18 kilonewton meters. This is your moment of resistance. Okay. So let's take the problem 22. That is the design problem. These previous 3 problems were related to the analysis part. We were calculating only that limiting moment of resistance. But in this case, we are going to calculate that what should be the area of the steel required, corresponding to actual location of neutral axis. Not limiting condition, but we are going for the actual value. So that's the design part. That is the design problem. So let's take the design problem. That's your problem number 4. It's saying we have a effective width of flange that's 2500 millimeters, and there's some effective flange. There's some flange width also. Flange thickness of DF 150 millimeters. We have some width of BW 300 millimeters. We have some effective depth of D 900 millimeters, and we have some steel that we need to get. That is the design problem. The design problem is that design this section, flange section. That means we need to get the AST. That is the design part. Is there any data related to the characteristic strength of materials? I think the material is M20 and steel is Fe415. Okay. We need to get the area of the steel reinforcement. Okay, let's take that. Now what's the moment we're applying on the section? Yeah, we need to see what is the moment we're applying on this cross section. Let's say the neutral axis is somewhere here. We're applying a moment of M working moment is applied equals to 1600 kilonewton meter. 1600 kilonewton meter. But we need to calculate the factored moment because we are calculating when we are designing in the limit state of flexure, we have load combination of 1.5 the dead load and the live load. So your factored moments would be equals to MUE, that is 1.5 times working moment, that's 2400 kilonewton meter. This is our MUE. Now we have to assume, now to get the AST, we will equate MUE with the actual value of moment of resistance and at the rate of XU, actual. And once I got the XU value, then I can get the value of AST. So for that, I have to assume that neutral axis is somewhere. So first step is that assume neutral axis somewhere. Let's assume that neutral axis is in the web. Let's assume first case that neutral axis was in the web. That it's a guesswork. You can assume any of the three cases directly. If I assume any of the 3 cases directly and that particular case was true, so you are safe. That means your time would be saved. You would get the answer solution very quickly. That's the trick. Yeah, that's the luck you can have. You can assume any other. You can assume any data. You can assume that neutral axis is somewhere. Let us assume that first case neutral axis is in the web. Let's see that where is the neutral axis. So I want to see whether this is true. So what is the moments we are applying? I'm going to equate external moments with the moment of resistance corresponding to that neutral axis is in the web, is in the flange, sorry. Yeah, we have to write it is in the flange. It's in the flange, first case. Yeah, 2400 kilonewton meters. Let's write that. 2400 kilonewton meter should be equated to, when I said that it is in the flange, that means your section would be in this fashion. That means BF is accounted here. So for that C force, we would write 0.36 FCK BF. What is the value of BF we have? What is the value of BF equals to? 2500? Yeah. BF equals to 2500. Let's write here. 2500 into XU. I don't know the value of XU. Then I know one thing, that's D minus 0.42 XU. D minus 0.42 XU. So I got the equation, quadratic equation here. I got the equation, quadratic equation. Let's see how to calculate here. Go for the equations in the calculator. Go for the equations in the calculator. Let's see how we can solve it. And write the quadratic equation ax square bx plus c equals to 0. Then we write, let's write that here we have negative value of xu square. Do you see that we have negative equation of xu square? Xu square. Let's write that. I would say minus 0.42 into 0.36 into 20 into 2500. This is your xu square. This is your ax square. Then after that we write that bx, value of bx is that 900 positive into 0.36 into 20 into 2500. This is your b. Okay, then we have negative c, because we have the equation of ax square plus bx plus c equals to 0. So your c becomes negative minus 224 minus 2400 into 10 to the power 6. We have to write here 10 to the power 6 also, because we are solving for Newton millimeters. So I would get a value that x can be either equals to 1982.7 or it can be equals to 160.11. 160.11. Yeah. Now I would say this value is not possible, because our total section is entirely your total depth of D is small d equals to 900. So first value is not possible for our calculations. I would say this should be possible location. But if I compare it with respect to DF, I would say your DF was actually 150. DF was 150. So, but my assumption was that XU was actually lesser than DF. My assumption was this was my assumption, XU less than DF, but I got XU greater than DF. So that means the assumption is not true. Assumption is not true. Not true. Assumption is not true. So I had to go for the second assumption, that neutral axis is in the web. So I have to assume now neutral axis is in the web. Let's erase this now. I would say neutral axis would be in the web. Neutral axis is in the web. Neutral axis is in the web. Is in the web. And one more condition is that we can say that 3/7 of XU. Let's say that 3/7 of XU. Let's calculate for. Let's try to calculate for that 3/7 of XU is less than DF. That means we are going for the calculations of YF. If this was your DF, and variation of the stress is in this way. So that means we need to convert it in terms of YF. So I would say your 3/7 of XU is less than DF. So we need to calculate in terms of YF, where your value of YF is equals to 0.65 into DF plus 0.15 XU. And that is equals to, let's solve it further, 0.65 into 150, that is 97.5. So 97.5 plus 0.15 XU. This is our value of YF. So your moment of resistance, I'm going to equate with the MUE external, that is 2400 kilonewton meters, and that should be equals to the equation we have, C1 Z1 plus C2 Z2. So 0.36 FCK BW XU and D minus, yeah, D is actually 900 D minus 0.42 XU. Then one more part is there, 0.45 FCK, and we have BF minus BW, BF minus BW, BF minus BW, BF minus BW. Okay. Then we have that YF. The value of YF is 97.5 plus 0.15 XU. And after that, we have one more part, that is D minus YF by 2. D minus YF by 2. YF by 2, that's 97.5 plus 0.15 XU divided by 2. So firstly, we need to solve this part. We need to solve this part. We need to solve for this part now, because it's having how much parts itself? It's having 4 parts, so we need to solve 97.5 into 900. Then we have one more part, that's 97.5 into minus 97.5 divided by 2. Then we have one more part, that's negative 97.5 into 0.15 XU divided by 2. Then we have one more part, that's 0.15 XU into 900. Then we have negative 0.15 XU into 97.5 divided by 2. Then we have one more part, that's negative 0.15 square XU square divided by 2. So we got 6 parts. We got 6 parts here. Now we need to convert in terms of, we need to convert those in terms of what you call as those some values. Let's solve this part also. Let's solve this part also. I would solve this part also. That's 0.45 FCK into 2200. We got this value as 19800. So this part is 19800 into this factor of 6 terms. We have these 6 terms, and first constant value comes to be equals to, let's solve this part, 97.5 into 900. This is 87750. 87750. Okay. And solve this part also. We can directly add these two we can add these 2 terms directly. Let's solve that directly. I would say minus 97.5 square divided by 2. So I got final value of 82996.87. So this part is over. This part is over now. This part is over. And we want to see whether there is any other constant. No, there is not any other constant. So I have this part, that is 82996.8750. So I'm going to multiply that with the actual value we have with this 19800. So finally I'm going to write those parameters now, final parameters. So I'm going to multiply this value with the 19800. 19800. So that is some value. Let's say that is some value. This value, this into this, we got some value, and I am going to subtract that from the other side. I'm going to subtract that from the other side of 2400. From this side we had some 2400 into 10 to the power 6, and I'm going to subtract that value we got from the calculations, that value, and I'm going to subtract that value, 2400 into 10 to the power 6, and minus this answer, what we got, minus this answer. So that finally is equals to, this answer finally comes out to be equals to constant of C, that is 756.6619 into 10 to the power 6. This is some constant of C, final C. This is equals to, so I would say this part is over now. I'm going to remove this part now. This part is over. Constant part is over. Now I would say, what is the linear portion we have? What is the linear portion we have in this one? I would say your linear variation of x is this one, and this is also linear variation, and this is also linear variation. So let's sum all those terms. I would say 97.5 into 0.15 into 0.05 into 0.5, and this is all negative, so minus times I can write minus times of all that data, all that data, it is negative times. Then we have positive 900 into 0.15, that is positive. Then we have negative 0.15 into 97.5 divided by 2. So I got value of 120.3750. So I got the value as 120.3750 XU. So I have to multiply it with the 19800. I have to multiply it with 19800. That's 2383 and some value we got finally. Some value we got. Some value we got. Then I have to add also here from the first term the linear variation of that. This is the first one. That's the linear variation from the first term we have. So I have to add that also. 0.36 FCK into 300 into 900. So finally you got value of 4327425. Let's try that. 4327425, and that's in the form of XU. After that we have the quadratic finally. I have the quadratic part finally. I would say we have 0.15 square divided by 2. Okay, this is all negative. This is all negative. And we have the factor of 19800. 19800. And we have to add also one more term, that's negative part. We have to add this part also. So I would say this is also negative 0.42. I would say minus 0.42 into 0.36 into 20 into 300. So that's negative 1129.95. So negative 1129.95 XU square. Let's hope for the best. Let's hope for the best that the value I would get, that would be also true. So I got the equation that let's say this is some ax square plus bx and plus this is your minus c. Let's keep it in this side. So I'm going to erase this part. Let's say this is positive and this is some negative value, and finally it equals to 0. So I'm going to solve for the quadratic equation 5 and go for the quadratic. That is negative 1129.95. After that we have to positive value of b, that is 4327425, and we have the negative value of c 756.6619 into 10 to the power 6. I hope that calculation will be easier and the answers would be coming to be true. Let's see. Yeah, XU, we got one of the value as 3646. That's not true. And second one, we need to check what is the X2 value. We have 183.66. We want to see whether this is true as per the calculations we have in the problem. We need to see that now, whether our calculations are true or not. I think it's not true. 183, yeah, 183.66 is true. 183.66, we got the final value. That's true. This is true. So this is the value we got, and that is true. So our calculations were correct. Long calculations. So these were correct. Now we need to check now whether this is as per the assumption. We need to see whether this is 3 by 7 of XU is as per the assumption. Let's solve that. Let's solve this value, and this is coming to be 3 by 7 of XU is equals to, let's see what is this value coming to be equals to. So 3 by 7 of XU is equals to 78.711 millimeters, and I need to compare it with respect to DF. See, value of DF is 150, and I would say this is less than DF. So if this is less than DF, and I would say, what was the assumption I had earlier? What was the assumption we take? We take the assumption that 3 by 7 of XU was less than DF. That means we used the equation of YF, and as per calculations we also got that true. That means you assumed the thing you assumed that is true. So we need to finally calculate now that moment of resistance corresponding to this one. Yeah, so that means we can further proceed. We can proceed further. Okay, we need to get the area of the steel. Now before that I had to say calculate the limiting condition. We need to see whether the section is reinforced under or it's under over reinforced. What is the limiting condition we have? Is it 0.48 times 900? 0.48 times 900? I think so. So that comes to be equals to 0.48 into 900. That is 432. This is 432 millimeters. That is greater than XU we got. The value of XU we got 183.66. That means the section is under reinforced section. So your steel can be calculated corresponding to the actual value of XU. Let's solve for the steel value. Let's solve for the steel area. So how can you solve for the steel area? I would say go for the summation of forces X equals to 0, C equals to T. That means 0.36 FCK BW XU actual, and we have plus 0.45 FCK BF minus BW, and we have that YF that is equals to 0.87 FY AST. That AST we need to calculate. And what was the value of YF? The value of YF is equals to 0.65 into 150 plus 0.15 into actual XU. XU is 183.66. 183.66, and value of XU is I have to substitute here 183.66, and the value of YF I have to substitute here, and value of YF is actually 125.05. 125.05, that is less than 150, that is DF. So this is also true. Okay, get the value of area of the steel. 7956.5 millimeters square is your area of the steel required. Now, once I got the area of the steel required, 7956.56, so I can now say we can have the limits. You can check for the minimum area of the steel. Minimum area of the steel is 0.85 by Fy into B times D. But here we take B as BW and D as that 900 effective depth. So corresponding to this one, we need to say what is the total value we have. BW we have 300 and D was 900, Fy was 415, and that value is equals to yeah, I have not checked that. You can see that how much value we have, and that would be less than AST provided we have. This is the AST required. We are going to provide a bit more, so that I would say that's okay. That means that AST provided would be more than limiting condition minimum value, and AST maximum is equals to 4% of B into D, where your B is actually width of web and D is that small d plus effective cover. This is 900 plus effective cover of, let's say 50 was there. We can assume 50, and that is the calculations we can have. Yeah. So this is your 4%, and it comes out to be 11,400 millimeters square. And I would say this our steel area should not be more than this, but we got only 7,000 something. We got 8,000, let's say. So that's also safe. So we can say okay, no problem. Now we need to take one more example. That's example number 5, or we can have problem number 5. Then we have 2 more problems. Let's take that problem now. Let's try to have this problem. Let's try to take this problem. Is it problem 5? I think. So it's given that we have a floor, T-beam floor. Let's have that. So this is our floor, and we have what you call as beams. Beams are also placed there. We have beams there. One beam is here. One more beam is here. Let's drag it. So one more beam is here. 1 2 3 4 5. 1 2 3 4 5. So let's say these are our beams, and all other part is that's your slab. So this is slab and beam, slabs and beams. So this is your, if I cut a section, let's say this is our section we are going to cut. Let's say this is our section that we are going to cut. Okay, this is our section, and I'm going to show that section AA. Let's say this is our section AA. Let's have this in this way. Sorry, Let's have this in this way. So this is our section AA. This is AA section. And I would say the detailing is that we have beams. The beam center to center spacing is that the center to center spacing between the beams, center to center spacing between the beams, beam is equals to 3.5 meters. And we have an effective span. Let's say this is some split supported here. This is supported here. And I would say effective span L effective equals to 6 meters. Effective span is equals to 6 meters. And the wall, or we can say beam, thickness of the beam, or we can say thickness of the web is 300 millimeters. I would say this is equals to 300 millimeters. This is 300 millimeters. So we can say this is the web. In the flange portion we can say, in the flange beam we can say this is the beam where we can have this BW as 300 millimeters. 300 millimeters. And the thickness of the slab should be provided. Yeah, thickness of the slab is 150 millimeters. Thickness of the slab is 150. Let's say this is DF, 150 millimeters. Yeah, this is D beam floor. Okay. 3.5 center to center. Everything is perfect. Monolithic construction. Okay. 30 centimeter wide beams. That is 300 millimeters. Now, it's saying that the superimposed load on the slab. Yeah. On the slab, superimposed load. So it's mentioning that superimposed load on the slab. That's 5 kilonewton per meter square. 5 kilonewton per meter square. So we need to, for M20 FE 250, we need to design intermediate beam. So we need to design intermediate beam. Intermediate beam. So we need to design one of the intermediate beams that would be treated as a flange beam. Let's take any intermediate beam. Let's take this one. Let's take this one. I would say the intermediate beam would be some sort of this one, that it's having some part from this side, contributing area from one of the sides as 3.5 by 2, and from the other side also. So if this is L1, I would say this is L1 by 2, this is some L2 by 2, and we have some BW such that this is your overall B, After that we can take BF. From this now we can calculate now BF. Okay. So this is our B. Now we need to get the BF also. I would say what was the question mentioning? Yeah, we need to design this intermediate beam. Now what do you have to design? If this data available is there, what do you have to design now? If the data is already provided to you, can you see what is the, can you tell me what is the, can you find what is the thing that we need to design? What's the data that is missing in this beam? If it is subjected to loads that develop those bending moments, can you tell me? I think we need to design for the area of the steel. So some steel should be provided here, so that we call as AST. And some more thing is there. Can you tell me? If I separate that particular T beam, let's separate that particular T beam outside. There's some B capital, there's some total B, and there's some DF, that's 150 millimeters. This was provided to you, and B was coming out to be equals. Can you calculate value of B? If the center to center 3.5 is there, if there is 3.5 center to center, that means let's try to calculate that. Can you tell me what is this value equals to? That's clear to clear span between those beams. This is not center to center. So we have to subtract some thickness. We have to subtract some width. So I would say this is equals to 3.5 minus 3.5 minus some value, that is 0.3. So 3.5 is theirs. So this is 3.5. Can you tell me that this is 3.2? And since the structure is symmetric, I would say that L1 by 2 is also equals to L2 by 2. L1 by 2 is equals to L2 by 2, and L1, where your L1 is equals to clear span, that's I would say that is equals to 3.2 meters, which implies that L1 by 2 is equals to L2 by 2, that is 3.2 by 2. So finally I would say L1 by 2 plus L2 by 2 is equals to 3.2. Can I say that? 3.2. I think I can say that. 3.2. 3.2. I think we can say that is 3.2. So if this is 3.2 plus we have this width of 0.3, so finally I would say B equals to 3.5 meters. So B equals to 3.5 meters. I would say that B equals to 3.5 meters. 3.5 meters or 3500 millimeters. And also I know the width of the web, that is 300 millimeters. Can you tell me what should be the design we need to design? What we need to design now? Area of the steel we need to design, okay? Is there any other data we have to get? Let's say there's some clear cover, there's some effective cover. So we need to design the effective depth also. We need to design this D, or we can say capital D also we need to design. So we need to design that what should be the depth of this beam, flanged beam. So we need to design D also. One is the area of the steel, next one is that depth of the beam. Let's go for that now. Finally you got the problem. Now we need to solve for the loading. What are the loadings that are provided, that are going to be produced, that are going to produce that bending moment on this beam of T beam, okay? Intermediate T beam, intermediate, flanged T beam. What are the loads? One of the load is that we have superimposed load that's coming from the external sources. This is coming from the external sources on the slab itself. So if there is slab per meter square, we are applying 5 kilonewtons. So this is one of the loads on the slab, and there is some thickness of the slab also, and its load is also in that fashion. Also we can say this is some per meter square of the slab also dead load, and that entire load is transferred for this effective span, for this effective area, I would say this is your contributing area to this particular beam. This is the total area of the slab that is contributing this total imposed load of 5 kilonewton per meter square. And one more intensity is there, self weight of slab per meter square. So these two loads are applied on the beam, and I would say the beam is also having some self weight also, beam self weight. So we had 3 different loads here. So we need to calculate 3 different loads for this beam. Let's try to calculate what is the total loads. What are the total loads on the slab? If this is the slab, what is the effective span? What is the effective span for that one beam? If there was one beam, how much slab part is taken by one beam? Can you tell me? Is this the total part of the slab that is taken by one beam? Is this the total part of the slab that's taken by one beam? So this part of the total slab is taken by one beam, and its extension is for the length of effective span from the back side. So this part of the total slab is taken by this T beam. So there is some T beam, and on this beam I am saying that the slab, one is the slab weight, okay, and next one is that one of the weight is slab weight, and one of the load is also applied at the top of the slab. So let's solve for that. So calculation of total loads and slab, total slab load, I would write as W all on slab. That's one is your imposed load on slab plus one is your self weight or dead load of slab. Can you calculate those values? Can you try to calculate those values? I would say imposed load on the slab is 5 kilonewton per meter square, and if I say what's one more load per meter square for the slab, is that gamma times thickness. If I take 1 meter square of the slab from the top, if I take 1 meter slab thickness of the slab, if this is 1 meter square of the slab, this is 1 meter slab, 1 meter square slab area, and there would be having some thickness of slab as 150 millimeters. So I would say gamma times that is concrete 25 into 150, 0.15, 0.150, and this is in terms of kilonewton per meter square. Then I have to multiply it with the total effective contributing area for one beam. So this width is, effective width is, I would say, that is 3.5 meters. That is actually a clear center to center beam spacing, 3.5 meters. So I have to multiply that 3.5 meters. So that total load of the slab is transferred to one of the beams. So let's calculate that value. 5 plus 25, 5 plus 25 into 0.150. That's 8.75 into 3.5. That is 30.6. So so total loads on the slab, that is 30.6250 kilonewton per meter. And I'm going to say what is the self weight of the beam. See, this part we have already calculated. The weight of dead load of slab we have already calculated. Now we need to calculate this part. If this was thickness of 150 millimeters and there is total depth of D, I would say this part of the web dw would be equals to D minus 150 millimeters, and there is some width of BW that was given to you as 300 millimeters. So I would say, what is the dead load of this? What is the dead load per meter? What is the dead load per meter for this what you call as web portion? So that is gamma times, I would write 25 kilonewton per meter cube into 0.3 meters into D minus 150 divided by 1000. So we need to say what should be the value of D, because we are going to design that value of D. So do you know any general thumb rule for the beams? If the effective span is 6 meters, from this side there is some effective span of 6 meters. Can you tell me what is the general thumb rule we have for the calculations of D? We take, if D is almost equals to 10 times that, or 12 times that, LE by 10, that is 6 meters divided by 10, that's 600. So if the capital D is 600, so your small d would be 450. So I would say I would say this value would be equals to 0.45 meters. 0.45 meters finally. I think so. 0.45 millimeters. Yeah, 0.45 meters. So finally I would get a value of 25. Then 25 into 0.3 into 0.45, that is 3.3750. This is the load of beam, dead load of beam per, this is intensity, kilonewton per meter. So finally I would say I am designing a beam. What is the total loads on the beam? So W all would be equals to W all on the slab plus W dead of the beam. So that is some 3.3750 plus some initial value of what we earlier calculated as 30.6250. So you have to sum them. 30.6250. 34, finally value of 34 kilonewton per meter. So this is the total loads. So can you get the, if you have a beam that is simply supported between two spans, simply supported between two supports, there is UDL of W equals to 34, maximum bending moment WL square by 8. So MUE can be solved as 1.5 times W L square by 8, that is equals to 1.5, that is 1.5 into 36 by 8, that is 229.5. That's total loads, total moments of 229.5 kilonewton meter. So this moment has to be resisted by that flange section, intermediate section. So we assumed that capital D was 600 millimeters. So this is our assumption. Okay. Can you tell me from this one what is the small d we can get? Can you tell me what should be the small d we can take? Let's say that effective cover is 50. So your small d would be 450, yeah, 550. And corresponding to that, let's calculate that. Now we had to assume that where is the neutral axis. So question starts now. Now the question is going to start. So we would say, where is the neutral axis? Where is the neutral axis? Now, finally, we got all that stuff. Now we have to calculate where is the neutral axis. Where is the neutral axis? So let's go for the neutral axis. So this was, yeah, we forgot one more thing. When we calculated B was equals to 3.5 meters, okay, then we had to calculate effective flange width. So for that, since your structure is continuous, which of the equation we had to use for the T-beam calculations? Which of the equation we had to use? So BF is equals to, we had to solve for BF equals to, where is this equation? Yeah, L naught by, yeah, that's BW plus 6 times DF plus L naught by 6. So BW was 300 millimeters. DF was 150 slab thickness. Then we have L naught. What is the L naught? This is the that distance between points of zero moments. Where the moment is zero. So for assembly support, what is this effect L naught equals to? Is that effective length 6 meters? So substitute 6,000 divided by 6 millimeters. So you would get a value of 2200 millimeters. 2200 millimeters as your BF, and that should be less than that initial value of B, that was 35. So your value should be finally BF of 2200. So let's remove this one. I am going to say your BF is equals to 2200 millimeters, and there is some thickness of flange as DF 150, and there's some steel somewhere here, and total depth is D, and there is some small d, effective depth as small d, and there's some width of the web as 300 millimeters. So this is our design problem now, and we are applying how much bending moment? We are applying? MUE was equals to 229.5 kilonewton meters. So for this moment, we have to design this beam. Let's assume that neutral axis is in the web. Let's assume, so assumption starts. Assume XU is in the web. So that means we are going to say XU is either less than or equals to 150 millimeters, because your DF is, yeah, in the flange, sorry, because your DF is 150. So based on this one, let's equate that moment 229.5. That is 229.5 in 10 power 6 Newton millimeters. That I am equating to the equation. Once I said that neutral axis is in the flange, what is the equation for that? That's effective compression area is only this part with the dimensions of BF into XU, because this is neutral axis. So the stress block is in this fashion. This is our stress block with the C force of C equals to 0.36 FCK times B XU, where your B is BF. And we have some T force also here, 0.87 FY AST. So let's go for that problem. Let's solve that. I would say 0.36 FCK BF into XU into D. Yeah, I don't know the value of D, but I assumed that capital D was 600, and based on that I had assumed that small d is 550. So 550 minus 0.42 XU. So we got one quadratic equation. Let's solve for the value of x. And you might be getting some value closer to 25 to 30 millimeters. Let's try to solve that. Let's have the equation, equation, and go for the quadratic parabolic equation. That's ax square, the x square. Let's solve that. Minus 0.42 into 0.36 into 20 into 2200. This is negative. Then finally b is your 550 into 0.36 into 20 into 2200 equals to, then we have c as negative 229.5 into 10 to the power 6. So let's go for that, and you would get a value of 26.89. So your neutral axis comes out to be equals to x equals to 26.89 millimeters. And we need to see whether this is true or not. I would say your value of x is less than df. So assumption is true. Assumption is true. If the assumption is true, so we need to say what is the limiting condition for your neutral axis, that is k times d, and your value of k is corresponds to your steel is Fe250. Your steel was given to you as Fe250, so your k value is 0.53, and d you assumed as 550, so that is that is greater, I would say that is greater than xu, so under reinforced section is there. So let's solve for the calculations. Let's solve for the value of AST now. So I would say that your d is sufficient. Your d provided is sufficient. Let's solve for the value of AST now. Let's solve for the value of AST now. So AST can be solved from summation of forces equals to 0, C equals to T, 0.36 FCK, BF was 2200, and XU value was 26.8954, that equals to 0.87 FY AST. So AST would be equals to, what is the value of AST we have? 1917.48, 1917.48, 19. This is almost equals to 1917.48. There might be little bit variation, so let's forget that. That's not a big issue. 1917.48, and corresponding to that, corresponding to this equation, let's solve for the actual value. Let's solve for the actual value. Let's try to solve for the actual value. 0.36 FCK BW BF XU, and this is your value, and divided by 0.87 FY, 0.87 FY, 1958.73 millimeters square. What was the earlier value we have? That was 1917. So this one is bigger than that. So let's select this value. Let's select this value. So now we have to select the bars. Let's say there's some bars of diameter. Let's select 25. If I select 25 bars, 25 diameter, so I would say let's try to select 25 bars. 1958.73 divided by 0.25 into pi into which bar I have selected, 25 square. Okay, so I need 4 bars, that is 3.99. that means I need 4 bars, so I'm going to select 4 bars. That can be solved as 1958.73 total area of the steel required divided by pi by 4 into 25 square. That's almost equals to 4, so I would select 4 bars. Then corresponding to the area of the steel provided, what is the area of the steel provided? That is 4 times pi by 4, 25 square. That is equals to pi by 4, 25 square, yeah, into 4 times. That is 1963, 1963.49, 1963.49, 1963.49 millimeters square. Okay, I got this AST provided. Now I would say what are the limiting conditions we can have. So one of the condition is that AST minimum is that 0.85 BD by FY, where your B is BW and D is small d, that was 550, BW is 300, FY is your 250. Let's solve that. 0.85 FY, 0.85 by FY inverse into 300 into 550, that is 561. That is lesser, so 561, that's safe. So our product is more than that. And AST maximum also solved by 4% BD, 4% BD, BW. This is your BW, and capital D is your 600, and that comes out to be equals to 7200. That's more than the provided, so all those are safe. So finally, final design is that, final design, let's have that. So final design here is we have 4 bars, here. we have this we have these dimensions, like we have the dimensions. These dimensions were already provided to you. That effective width we have 2200, and we have small d equals to 550. We have effective cover of EC equals to 50. Here we have total d equals to 600, and your thickness of the slab is 150, and we are providing 4 number of bars, 25 diameter. This is your design of the section. Okay, let's take the one more problem. Let's take the problem 7 or 6. Okay, let's take the one more. Let's take one more problem. It's saying we have a T-beam. T-beam dimensions we have. This is your 100. This is your BF of 1200 millimeters thickness. Width of the web is 300. We are providing steel AST as 4 number of 25 bars. 4 number of 25 bars, and your small d effective depth, small d is 560 millimeters, and we need to calculate factored moment of resistance. And we have M20, we have FE415 HYSD. So let's go for that. So if we want to get the moment of resistance and area of the steel is provided, so I need to calculate actual location of neutral axis, and after that I have to calculate that actual moment of resistance at that location. So I have to assume that initially, let's assume that neutral axis is in the web. Neutral axis is in the web. Sorry, not in the web, is in the flange. That means I am assuming that dxu is either less than or equals to df. Let's assume that, and from that I would say your value of xu can be solved by c equals to t. So I would say total c force is equals to 0.36 fck, and bf, when I assume that it's in the flange, that means b corresponding to bf, that is 1200, and there is xu. This should be equated to 0.87 fy ast. What is the ast we have? 4 number of bars of area pi by 425 square. So this value xu comes out to be equals to, your xu comes out to be equals to 82.05. Your value of xu comes out to be equals to 82.051 millimeters, and that is lesser than df. Your df was 100, so that's true. That means assumption is true. If the assumption is true, that means you can proceed further. We can write true. That means proceed further. That means we can calculate limiting condition for that axial limiting neutral axis. That is 0.48 times 560, and that is greater than xu. So under reinforced section. So let's go for the moment of resistance. Moment of resistance of this section. This is corresponding to some CZ. Lever arm of d minus 0.42 xu. Let's solve that. Substitute the value of xu as that's 82.051. So this is 0.36 fck bf xu d minus 0.42 xu. So you can solve that, get the moment of resistance equals to 372.57 kilonewton meter. You can also solve it by 0.87 fy ast. This is your ast into that same value of d minus 0.42 xu, and you can get the same value of moment of resistance. Okay, let's take the problem, one more problem. Same data is there. We have the same problem now. In the second problem, let's take the second case of this problem. Second problem for the same dimensions, but where our steel is that we are using 5 number of 25 bars. 5 number of 25 bars. And based on this one, if the same data is there, then I assume that xu is in the neutral, xu is in the flange, and I need to get the moment of resistance. So let's assume that xu is in the flange. So I need to solve this. I would say 0.87 Fy AST, where your AST is 5 bars of pi by 4 25 square, and after solving it, you would get a value of xu equals to 102.59, and that is greater than df 100. So your df is lesser than xu, so your assumption is not true. So assumption is not true, so it is false. That means assumption is false, so we need to keep that neutral axis is in the web. So the assumption is that xu is in the web. So second assumption is that I am saying that xu is definitely in the web, but now the second assumption is that 3 by 7 of xu, either we can take it less than or greater than df. Let's take it corresponding to, let's say that that df is less. Let's say that df is less. That means entire part of the df is having uniform stress, 0.45 fck. So that means the equation would be corresponding to df. So let's equate that equation. Let's equate c equals to t for the calculation of xu. So I would say 0.36 fck bw was 300. bw was 300. Yeah. 0.36 fck bw xu plus c1 plus c2. c2 force was 0.45 fck, and the bf minus bw. And we have that df was 100. And that should be equals to 0.87 fy ast, 5 bars of pi by 4 25 square, and your xu comes out to be equals to 35.36 millimeters. Yeah, 35.36 millimeters. And but I assumed that xu was in the web. I assumed that xu is in the web, but I got xu that is lesser than df. It's not true. So that means there's calculation problem with that means the assumption we have, it's not true. That means assumption is not true. Calculation is true, but assumption is not true. So we need to say final location of neutral axis is such that your df would be, so final assumption is that your df is greater than 3 by 7 of xu. If this is df, your 3 by 7 is only up to this part. After that we have variation in this way, such that it becomes 0 in this somewhere here in the neutral axis in the web portion. If this was your df, your 3 by 7 is only here. So we need to get the equation of yf. So let's write that yf equation as 0.65 df plus 0.15 xu, and the value of df is 100, so this part becomes 65. So let's solve that equation. C equals to t for the third case. Now third case is that to get the location of xu, I am assuming that df is greater than 3 by 7 of xu. Let's solve for the value of xu. C equals to t, that is c1 plus c2 equals to t1 plus t2, and I would say 0.36 fck b times bw xu plus c2 force of 0.45 fck, and difference of those width bf minus bw, that is 1200 minus 300, and bf minus bw. Then we have yf, 65 plus 0.15 xu. This should be equals to 0.87 fy ast, pi by 4 25 square, and we have 5 number of bars. Do you got it? I think you can get it. So this is our equation. That your c1 plus c2 equals to t1 plus t2, 0.36 fck bw xu plus 0.45 fck bf minus bw, and yf, this is yf, and this is equals to 0.87 fy ast, 5 bars of 25 diameter. And corresponding to that, you would get a value of xu finally. So xu comes out to be equals to 106.63, and our assumption was that your neutral axis is in the web, and you got a value that is greater than df. So it's true. It's true. It's true. Now we need to see whether 3/7 of xu is greater than or equal or less than that df. Let's solve for 3/7 of xu, and this is coming out to be equals to 3/7 of xu is 3/7 of xu. That's 106.63. That is 45.69. 45.699, and I would say that is also less than df. And our assumption was that your df is bigger, 3/7 is lesser, 3/7 is lesser. So this was df level, this was df, and this is 3/7. So this is assumption is true. So final calculations would be proceeded further for this part. So final location of neutral axis is that you have xu equals to 106.63. So let's calculate limiting condition. That is 0.48 times d, and that is I would say that is greater than 106. So that's under reinforced section. So moment of resistance, we have the equation moment of resistance at the rate of xu, and equation is that using the concept of yf. So that is 0.36 fck bw is 300. Yeah, xu was 106.63 xu. Then we have d minus 0.42 xu. D value of d was 460. We have already calculated those values. Value of d, it was given to you d. Yeah, you should solve for the 560. Sorry, it was given to you as 560, so we have calculated for 560. So d is 560. It's not a big issue. So d is 560. So kindly change that in the previous solutions also, but the values, final values are correct. So that is 560. Okay, that's 560 minus 0.42 xu. 0.42 xu. This is your first part of the lever arm, that is C1Z1. That is first moment C1Z1. Because of that rectangular beam of dimensions BW and effective depth of D, such that your stress block was in this fashion. And lever arm of Z1, C1, Z1. This was C1 and this was Z1 lever arm. And plus 0.45. 0.45. Sorry. Yeah, some beam was there with the concrete section. This part was your concrete section. So 0.45 fck and bf minus bw, then we have the concept of yf, value of yf is equals to 65 plus 0.15 into xu, and we have the lever arm of d minus yf by 2. Substitute the value of yf here. The value of yf comes out to be equals to 80.995. So you have to substitute that value, and finally you can get the solution of MOR of the section. Moment of resistance of the section is this value. This is your answer for the problem, that is 459.49 kilonewton meter. Let's take the final problem for your flanged beams. Final problem for your flanged beams. Final one. We have the same beam. The beam is same. Flanged beam is same. Dimensions are same. So this is the third case of this problem, that BF is 1200, thickness of flange is 100, width of the web is 300, and area of the steel is now changed to AST such that it is equals to 4 bars 25, yeah, 26. We have now 6 number of 28 bars. We have 6 number of 28 diameter bars. 6 number of 28 diameter bars, and small d is also same, 560. So all the data is same except that steel reinforcement has been changed. Let's assume that first case. So let's assume that first case, that neutral axis is in flange. First case, assume that this one. That means xu is less than equals to df. So let's assume that, and based on that, I can say C equals to T to get the location of XU. C equals to T. 0.36 FCK BF. This was 1200 BF into XU. That is equals to 0.87 FY AST. AST we have how many bars? We have 6 number of pi by 4 28 square. This is the area of the steel, 6 number of 28 bars. Then accordingly I can get the value of XU equals to 242.8 millimeters. No, it is not the assumption, this is not the true value. So let's solve it. I would say what's the condition we have. Let's solve for this one. 0.36 FCK and B is equals to, then we have 0.87 FY into 6 bars of pi by 4 d square 28 square divided by this answer we have, that is 154. So I got that XU value equals to 154.38 millimeters. But the assumption we have, that means I assumed that this is less than, but I got it's greater than 100. So assumption is not true. So this is false. That means neutral axis is somewhere in the web. So neutral axis is somewhere in the web. Neutral axis is in the web. In the web. So I would say if I calculate 3 by 7 of XU, let's say that 3 by 7 of XU is in the part such that, let's solve for this case that 3 by 7 of XU is it's greater than DF. That means if I solve corresponding to this condition, that means this is DF and 3 by 7 is up to this point. That means 3 by 7 is more. That means 3 by 7 is more. Okay. 3 by 7 of XU is more. Okay. Based on that, let's assume, and which of the calculations we have to take? I would say C equals to T and add the rate of DF equation. I have to use that equation of DF. So that means we have constant stress of 0.45 for the entire DF. So I have the equation of DF. So I would say 0.36 FCK BW, that is 300, and we have XU plus 0.45 FCK, 0.45 FCK, and BF minus BW, and we have this DF, we have this multiply of DF, and that DF is equals to 0. DF is actually 100, so DF is equals to 100, and that total C forces we have to equate to total T force 0.87 FY AST. 6 bars of diameter, 28. So this is your AST. And solve for that, you can get the value of XU. For this case, if you assume neutral axis is such that it is 3 by 7 of X is 3 by 7 of XU is greater than DF. Now I assume that DF is less than 3 by 7 of XU, and I got that XU comes out to be equals to 242.8 millimeters. And let's check now. We need to check now whether our assumption is true. Now we need to check 3 by 7 of XU, 242.8. So what is this value comes out to be equals to? And that is 104.06. 104.06. And is that greater than DF? Your DF is 100. Your DF is 100. So I would say your value is greater than DF, and it is true as per assumption. Assumption was that this value is greater than DF, so assumption is also true. So that means it's true. So that means we go for the further calculations. Proceed further. For what? For XU limiting. The value of XU limiting we already know, that is 0.48 into small d. So that's, I would say that is greater than, that's some 200 value. That's some value. That's more. That's more. That's more. That's 0.48 into 560. Let's solve that. 0.48 into 560. That's 268.8. That's 268.8. That's greater than XU. That is greater than XU. That's greater than XU. So yeah, we need to see that. We need to see. Yeah, your XU value is 242. So it is greater. So I would say your XU limiting is greater than XU. So under reinforced section, Now, final problem is that get the moment of resistance. So I would say moment of resistance at the rate of XU actual as using the calculations of equation of dF, that is the stress is constant. So that equation is C1Z1 plus C2Z2. So final touch is that we have the stress block here. There is some C1 force 0.36 FCK, some width of BW XU, and we have some T1 force 0.87 FY AST1, and such that this was your rectangular beam with the width of section as BW, and plus we have some imaginary beam, but there was some section, concrete section was there with the dimensions of DF, and this was total part was equals to sum of these two was equals to BF minus BW, and there was some C force because of those two. There was some C2 force. C2 force was equals to 0.45 FCK, and BF minus BW into depth of DF, and there was some T2 force of 0.87 FY AST2, and the lever arm Z2 was D minus dF by 2. This was dF by 2 centroid of that force. So let's solve that. Total moment of resistance. So I would say moment of resistance of this problem is equals to C1Z1 plus C2Z2. So I would say 0.36 FCK into BW into XU actual. The actual XU we got some 244. The actual XU we got 242.8, 242.8, 242.8, 242.8, and we have that D minus 0.42 XU, and we have D minus 0.42 XU, and then plus C2Z2 0.45 FCK, and BF minus BW, and we have this DF of 100, and we have that lever arm of 560 minus DF by 2. So finally, this is your solution for the problem, and get the value of moment of resistance equals to 653.31 kilonewton meters. So this is the end of all those solutions. Thank you for watching our series of that RCC from the concrete path, where the content is everything, tons of problems. So thank you for watching our series. Okay.